I will introduce our first speaker. So Jean Raynaud will the first speaker to hit the stage. So a couple of words to introduce Jean. Jean was appointed as a senior research scientist in the C2P2 laboratory in 2013 after his thesis in Bordeaux University, LCPO. In 2010, he got a postdoctoral position in the Ritter Group at Harvard University on a Marie Curie IOF grant. His expertise ranges from polymer chemistries to organic and organometallic strategies for catalysis. His current research focuses on sustainable catalysis for polymerization with an emphasis on iron and dynamic polymers with energy storage capabilities, as well as on depolymerization chemistries. Circular economy and energy matter efficiency are thus at the center of his research towards sustainable polymers. He has partnership with several industrial companies and several international collaborations. He has co-authored more than 40 research papers and 25 patents. So, Jean, we are really happy to have you today. Thank you very much for coming. The stage is yours.
Thank you very much, Sylvain. Thank you for the invite. Thank you for the invite. I'm very happy to be here. I'm going to try to introduce to you the concept of polyolefins, a little bit about their synthesis, generally speaking, about the history, how we came to using a lot of catalysis for polyolefins. And at the end of my talk, I will present a few research projects ongoing in our lab. One dedicated to the understanding of the catalytic active site of Ziegler-Natta polymerization, and one regarding maybe how to deconstruct polyethylene chains to valorize, to do a little bit of upcycling. So we'll discuss this at the end. So I work at the CP2M lab in Lyon. It's a lab which is focused on catalysis and in particular at the service of polymer science. And we work both on making polymers and more recently on recycling them. I want to thank a couple of collaborators, and I will thank a lot of people at the end. So the students, of course, without them, this work and this presentation couldn't exist. So Adamou, Felipe, and Mathieu, I would present their results. Sébastien, David, Alexander, and Christophe for a lot of insight on techniques that can be applied to understand Ziegler-Natta catalysis. My long-term partner, Vincent Monteil, for a lot of things, a lot of input, teaching me a lot about polyolefins in general. Okay, so this is just a quick reminder. So nowadays, well, these are numbers that are, now it's upwards of 400 million tons, but in 2021, it was about 390 million tons, and 90% of them come from fossil-based. Okay, and these account for. So 90% come from fossil-based resources, and a small fraction only is recycled. Okay, it's about 8 to 9%. And right now we are approaching the 2% mark regarding bio-based polymers and so-called plastics most of the time. Okay. We will discuss that a little. So just a reminder, this is really for thermoplastics in particular, but these concepts, they do apply to polymers, generally speaking. So if you want to develop a new polymer, you have to remember a couple of details. Okay, so you want the physical properties. These are ideally tunable. They can really focus on the mechanical properties, but it can be really like specific properties. You want something that is easy to process, ideally on very large scale. So something that ideally you could extrude is interesting, and that you can also produce very easily with without resorting to solvents, for instance. Okay. Of course, there is the economical issue. So you want easy access to monomers. So very few synthetic steps, ideally speaking, and you want no toxicity, or at least you need to take into account all these factors. The chemistry for the synthesis should be very easy to scale up, because you want to be able to sell your product, and you need to take into account all the associated costs, environmental costs, but also anything that surrounds your process. Okay, so ideally no solvent, minimal side products, and things like that are highly desirable. Okay, and just a comment: the most important polymers at the moment, polyolefins, they account for more than half of the 400 million tons. So it's about 220 million tons at the moment. Okay, so polyethylenes and polypropylenes, and then you have about 30 to 40 million tons for PVC, PS, and PET. Okay, and these are really thermoplastic materials. Usually speaking, like the cross-linked materials, and they account for a much smaller number. But we'll discuss what is really the definition of a thermoplastic, because it's somewhat cross-linked, but physically cross-linked. So this is the key, right? I'm talking about physically cross-linked, and it's particularly true for semi-crystalline polymers, and in particular polyethylene and polypropylene. Okay, so you'll have a melting temperature, and you'll have a crystallization temperature, and of course you'll have a glass transition temperature. But in the case of polyolefins, they are rather low, and in particular for polyethylene, okay, you can give a value of minus 100 something. A lot of debate in the community about this actual value, so I'm not going to comment on that too much. But what you need to remember is, yes, you have a glassy state, but you also have crystalline parts, and because of these crystalline parts, then you have some toughness and a lot of interesting mechanical properties. They come from this semi-crystallinity. So just a comment: for P crystallization, we talk about lamellar structures. For PP, it's more like helical organization, and these chain regularities that you can get when you do the synthesis of these polymers allow you to get these semi-crystalline properties. The range of crystallinity is usually between 30 and 70%, and this gives you, for an HDPE of 60 to 70% crystallinity, a melting temperature of 135, and for PP, an isotactic PP, 99 something percent, obtained by Ziegler-Natta strategies, 165 degrees. This is the reason why usually when you want to sterilize something, you will go to isotactic PP rather than PE, right? Okay. A couple of comments regarding the molar masses. So most of you know that in order to get like final mechanical properties of polymer, you need to reach a certain molar mass, and it's usually linked to entanglement, chain entanglement. And just a comment, when you have oligomers, when you haven't reached the entanglement, you have like barely a polymer behavior. And then once you reach the entanglement, that's when you maximize your mechanical properties and everything that comes with the polymer behavior, okay, and a non-Newtonian behavior, for instance. And of course, you need to find a compromise, because if you reach very, very high molar masses, you tend to have a difficulty to process the material. So you want, yes, the best mechanical properties, but you still want something that's going to be injectable or processable at least. Okay, so this is also something to bear in mind. A comment about entanglement. for polyolefins, it tends to be the value of molar mass to reach the entanglement tends to be very low. So you get this semicrystalline polymer very early, okay, and that's a big advantage. So you'll get an entanglement for PE for something that most of you would qualify as, oh, it looks like an oligomer. 4,000 grams per mole is not a high number, but already you start to see like an interesting, for instance, an HDP of 4,000 grams per mole as already a melting point of almost 132, 33, so almost 135, okay? So just a comment, if you have like a molar mass of for polyethylene of 10,000 grams per mole, you have one macromolecule entangled with 10 others. So it's just to give you a rough idea. And if you have 1,000,000 grams per mole, then one macromolecule is entangled with roughly 100 others. And that explains why you have such different properties in the melt, for instance, or on the final product. So yes, a comment on the molar mass distribution. So a lot of people would tell you, I do controlled radical polymerization. I want to aim at a 1 in dispersity or close to 1. Okay, if you do polyolefin, polyethylene processing, you don't want that. Basically, you want something a little bit broader, where you have like high molar masses and a little bit of a tail in low molar masses that will help your processing, especially for extrusion or injection molding, for instance. Okay. So yeah, what about really specifically looking at polyolefins? So if you look at this pie chart, you will realize, okay, polyolefins, they account for more than half. Okay, so we should know how to make them on a very large scale, and we should understand, I mean, why it's the catalysis can influence all the properties, and at which stage we can influence the final product. Okay, so that's the purpose of this first part of the presentation, to give you some hints about where I can act to change the properties of my polymer. With a strong emphasis on chemistry, because I'm a chemist and not so much a physicist. Okay. And a quick comment. I discussed, so on the first slide, you saw catalysis, because I really like catalysis, and because also polyolefins are usually made by catalysis, more than 75% are made by catalysis, okay? But there is still LDPE, the case of LDPE. It's historically, it's actually the first one to be produced, right? 1933, ICI, a company, they discovered that if you pressurize ethylene at high temperature, and you have a little bit of, let's say, peroxide impurities, a little bit of oxygen in your reactor, you will end up with low density polyethylene. Low density polyethylene is a little bit particular, so it's a radical process. There is no metal involved, okay? There could be, but it's not necessary here. And you have two phenomena that coexist during this polymerization. It's that will generate short chain branching and long chain branching. Okay, so you can have transfer, some kind of backbiting that would give you a C4 chain branching. Okay, but you can also do a transfer anywhere on the polyethylene chain. Okay, that would give you a long chain branching. These two things are very important, in particular the long chain branching, and it's because of the processing. Okay, the viscosity that the long chain branching gives you in the melt is so important, because it allows you to do, for instance, blowing type processes. Okay, if you don't have this melt strength, you will not be able to do that. So people claiming that with some LLDPE, you can match the properties of LDPE, it's not technically correct. This long chain branching is particularly important, okay? And the short chain branching, it's also interesting because it will reduce your melting temperature. It will make it very easy to process, and for all the wraps and everything, when you do packaging, it's so useful to have LDP. So it was just my small comment, and after that I will only talk about catalysis. So if people talk a little bit about polyethylene and polyolefins, generally speaking, the name of Ziegler is usually familiar to you because they won Ziegler and Natta the Nobel Prize for the development of the specific catalysis I'm going to talk about. Okay, so it's an interesting discovery, I would say, because they were not exactly looking for making polymers. They were more in the business for making short oligomers, and they were interested in the Aufbau process. So if you have tried ethyl aluminum, you pressurize with ethylene. You need a little bit of pressure, 100 bars, and you have some oligomerization process that takes place. And they discovered something that was coined the nickel effect. Okay, so if you have a little bit of nickel residues in your batch reactor, you will have an issue. You will not be able to fully oligomerize. You will have a beta hydride reaction with this nickel that will only allow you to go from ethylene to butene. Okay, that's barely an oligomerization. It's more dimerization. But when they realized that, they thought, oh, means that if I add a little bit of a metal, maybe I can tune that. Maybe I can go longer. Maybe I can be very selective for butene or whatever. So they started screening the periodic table, and they ended up with a mixture of titanium Tcl4, actually titanium tetrachloride, and triethyl aluminum in the presence of ethylene at low pressure. You don't need to go to 100 bars, and they ended up with polyethylene. And then a lot of development for copolymerization. They realized that they could add a lot of comonomers, and they will be able, with only ethylene, to produce HDPE, and then with the comonomer LLDPE, with therefore a lot of short chain branching. Okay. So this is the first actual polymerization of ethylene unit. It's a historical thing. You can see a lot of glass reactors, and there is a separation of the polymer because, okay, the catalyst loading, they were really, really high at that stage, okay? It was not supported catalysis. It was like a kind of starting as a homogeneous mixture, and then the polymer starts to precipitate and crystallize. Therefore, you have to somewhat separate the excess titanium that you have on your polymer at the end. Okay, so these are separation steps. These are more modern processes. Okay, it's gas phase reactor. This is very close to the unipole process. Okay, and it's a fluidized based reactor. So you have particles of catalyst. Okay, you pressurize with the gas. It's fluidized bed, and then the particle of polymer grows around the catalyst particle, and then you have a separation, and you can also separate the fines. You can recirculate. There are many now. This is like a simplified process, but it's just to tell you that this came to be just because we realized that we could support the catalyst, and I will explain to you how you can support this catalyst. So, just a quick comment. Depending on the process you choose to make polyethylenes, you can have the LDPE. So I really described it. The LLDPE with only short chain branching. So you can, but because you select the comonomer that you add with ethylene, you can exactly tune the length of the short chain. Okay. Here there are more C4 branches, but here you can have C4. You can also have C6 branches if you copolymerize with octene, for instance. And HDPE, mostly linear and a melting temperature. Okay, it can be slightly upwards of 135. You can reach 136, 37. It depends. Crystallinity is just, these are rough ideas that you can bear in mind. 40 to 50 for an LLDPE, for instance, slightly lower for an LLDPE, and 70% for an HDPE. And the density, of course, rises when you increase the crystallinity. this is just a visual thing that I got from the Nobel lecture from Carl Ziegler. It's just a picture. You have the HDP, and I don't know if you see the hand here, but they are just pressing two cups, one in HDP and one in LDP, and okay, you can tell that one has like better mechanical properties, and this is just the physical cross-linking because of this crystallization, because of these lamella. Then you get a much tougher material here. Okay. I'm not going to discuss PP too much, but I want you to understand why 97% of PPs produced worldwide is done by Ziegler-Natta catalysis and supported catalysis in particular. Okay, it's because it's so interesting from a supported titanium center that you can generate geometries by tuning the way you prepare the precatalyst that will allow you to both get a regioselectivity on the insertion of propylene, okay, and also a tacticity, so a stereoselectivity. And this allows you to get either isotactic, syntactic, or atactic polypropylene. And the one that most of you know is isotactic PP, okay, because it's usually the one that is used, okay, and it is produced worldwide. It must account for more than 95% of the total production, okay. Because you have this methyl, of course, this governs the chiral center, and then you can have isotactic or syntactic or atactic. So, and the big contribution to the Ziegler-Natta of Natta is isotactic PP, just so you know. So Ziegler is more responsible for the discovery of PE and the type of thing, and Natta, because he used the alpha Tickle 3, so titanium at the oxidation state 3, he discovered that you could get this isotactic PP. Quick comment: the density is not high, but the melting temperature is very high in the case of PP, and because the mechanical properties, they do increase with the isotacticity percentage. Okay, you really want to reach like 99 plus values in terms of isotacticity index. Okay, there is a way to determine that. So a quick comment. A chain polymerization is catalytic when the active center of the polymerization is able to generate more than one chain of polymer. This is very important. We're going to talk about transfer. There is no termination reaction of the active center during the polymerization. The reason is, I mean, sometimes they do get dormant, but you can reactivate them. There are tricks to do that. Maybe hydrogen can help you from time to time. Okay. There are many polymers that cannot really be made by another strategy. Okay, so in the case of PP, if you don't have a catalyst, isotactic PP out of question. Okay, HDPE is very similar. You need a catalyst to that, a metal catalyst, and you want the catalyst to be very, very low. You want very high activity because of productivity reasons, but also because the catalyst, okay, will be embedded in your polymer. You cannot really remove it in the end, especially in these semi-crystalline polymers. And there are some chain transfer reactions that can control. And I talked a little bit about hydrogen. Hydrogen is a very good chain transfer agent, so you can mitigate the molar masses this way. So what is a catalyst, and why do you call coordination, insertion, polymerization type strategies this way? Okay, so you have a metal, usually a transition metal. You have a ligand set. They can be organic ligands. We discussed a little bit metallocene type catalyst, but they can be inorganic ligands. Ziegler-Natta catalysts are usually supported on magnesium dichloride. A lot of these ligands are chlorine atoms. Okay, so ligands doesn't necessarily mean like these fancy I want to say CP star type ligands. They can be completely inorganic. You need a metal carbon bond, okay, or metal hydrogen bond. It works as well. You need something that is basically your needle, and you will start weaving. Okay, the whole, you will start knitting the polymer chain. Okay, And you have a coordination site for the olefin. Without this coordination site, forget it. You will not have any polymerization. Okay, you need basically your monomer to anchor to the metal and then get inserted. There are several metals that can do that. There are some that do that very, very well. So titanium, zirconium. And you can do that with like other metals. So vanadium, chromium. I will give you an example with chromium. Vanadium is more for EPDM, for the people who really know. And you can also develop with late transition metal. And I'll give you also an example of how you can do that with iron. Okay, so just for you, in a recipe typical for Ziegler-Natta, you'll probably have some Tcl 4, you'll probably have a support, and some aluminum alkyls, okay? Why aluminum alkyls? Because you need, a pre-catalyst is usually titanium with a lot of chlorides, okay? You'll need to make this metal carbon bond or metal hydrogen bond, okay? So you will need to alkylate. You need a transmetallation, and you at least alkylate once. But you will realize that titanium 4 is not ideal, especially for supported catalysis, and it's usually a titanium 3 that is needed. So therefore, you need also something that can induce reduction, okay? And there are also reducing agents, these aluminum alkyls. So these are two things that you need to remember. And then you can get very fancy, right? Especially if you want to design a pre-catalyst that upon alkylation and reduction will give you isotactic PP. If you want that, you need to add, like in the recipe, a little bit of internal bases. So it's to tune the surface of the magnesium dichloride support, okay? And then at the polymerization stage, you also need to add an external base, and this will tune the geometry of the active site to induce radioselectivity and seroselectivity. So I gave you some examples. So internal bases are usually phthalates and silanes for external Lewis bases. These are very standard strategies. So now people, they worry about the phthalates. So there are other type of diethers or things that are non-phthalate based. But the amount of phthalate that you would get in isotactic PP is so little because the catalyst residues are so negligible that I still don't really grasp this concept. Okay. A comment about catalyst performances. So Ziegler-Natta polymerization, they tend to have like one of the best productivity, especially if you take into account the fact that of the titanium that is on the solid support, that is your pre-catalyst, only few of them really turn into polymerization active site. So these are values that don't take into account the fact that you are only activating maybe 5% of the titanium, okay? But even if you take into account all the titanium that you deposited on the magnesium dichloride, you end up with values where you can produce like 40,000 grams of PP per gram of catalyst per hour. And values quite similar can be achieved also for polyethylene. Okay, a little bit lower most of the time, but in the 20,000 grams of PE per gram of catalyst per hour. Okay, so these values of per mole of titanium, they can reach 10 to the power 9. So that's pretty impressive. And if you know about like solution and homogeneous catalysis, these values are quite incredible. It means that you make one polymer chain every second, and the monomer insertion is less than 2 milliseconds, okay, about 1 millisecond for monomer insertion. The pressure can reach 35 bars, but mostly it's going to be at lower pressures, okay, slightly lower than that. And the particle size ranges from a couple of 100 microns to millimeters sometimes. I just want to mention Phillips catalysts that are very popular in the US, a little bit less on the European and Asian market. Okay, so Phillips catalyst actually predates. So this is the only correction that I don't have on my memory stick, but it actually predates even 1954. It's a little bit earlier than that. This is the patent, so they must have worked on that a little bit earlier. Okay, So Philips company, two guys, Banks and Hogan, and they started supporting chromium oxide on silica. So it's not magnesium dichloride, the support this time, it's silica, okay? In that case, the molecular weight, the molar masses are regulated by temperature. You have like a broad dispersity. You cannot really make things that are not ethylene based. Okay, so it's going to be mainly HDPE and a little bit of LLDPE, but no PP can be done. That's why it didn't grow as much as Ziegler Natta, and most people now use Ziegler Natta rather than Philips, except for like some very specific products of polyethylene. Okay, it's slightly less active than Ziegler Natta catalyst, and the activation process is less understood. So a lot of people think that it starts with reduction of chromium at higher temperature, and you have probably a chromium 2, and then oxidative coupling to create like rings on this chromium. And then when the ring tension gets a little bit too much, then you have a 3,7 hydride shift or something like that, and you will get a chromium hydride, and then you can start producing your polymer chains. Okay, so this is still up for debate. There are many research groups working on that, and it's not completely understood. This is analogous to what can be done for oligomerization on chromium. So that's why I'm just giving you hints how it works. And I will briefly discuss single-site catalysis, not because I don't like it. I find it completely fascinating. It's just because it doesn't work for so many products. It gives you a poorly isotactic PP with a melting temperature of 158, sometimes 60 if you're really, really good and you make like a very good and fancy ligand. But it has some advantages nonetheless, because you can, Ziegler Natta catalysis, the conventional one, supported on magnesium dichloride, is very heterogeneous. Okay, it's multi-site catalysis. You generate a lot of different active sites on the surface, and you hope for the best. Maybe some of them will die, the one that don't give you, for instance, a good seroselectivity. And then on the long chain, you'll have a site that does its job really, really well and gives you perfectly isotactic PP. So you have heterogeneity even in the products. But because of what I said about like the long chain being produced by a very regular site with perfect geometries and very active, then you don't care, because these will be just your process facilitators, the short chains, okay? And the long chains will give you the mechanical properties and the 165 melting point. When you have a single site catalysis, usually when you do things well and you activate really well and you have only one active site, it's not always the case. You can have, okay, something that does the job all the same, always the same. It will produce always the same kind of statistical errors in your isotactic PP, and therefore you end up with something more homogeneous, but most of the time the properties are lower. So it's going to be overall a slightly less, lower isotactic index. Okay, but you can get very narrow molar mass distributions, and sometimes it's interesting also to have like a, let's say, multimodal distributions for very specific mechanical properties, and this you can get with a mixture of metallocene or post-metallocene type catalysts. Just a little bit of history on metallocenes. One key discovery was metal aluminum oxide, okay, and this allows you to activate things such as zirconocenes or titanocenes, okay. So 2CP, 2-chloride will alkylate, cationize with MAO, and this will give you the metal carbon bond and the open coordination site, because it will be a cation, okay. A comment about MAO, there is a fascinating article in Science this year about the extractable aluminum cation, okay, and this is supposed to be the one responsible for dealkylating and making the cationic titanium 4 type species. So for metallocene, there is still debate. Is it like titanium 4, titanium 3? It's a little bit more. For supported on magnesium dichloride, I hope that I will convince you that it's more titanium-3. Yes, just a comment. Usually you put 500 aluminum for 1 titanium if you want a good activity. So it's just you're going to be consuming a lot of aluminum alkyls in this type of catalysts. A comment about the processes. So I mentioned high pressure processes only for PE. Lower pressure are usually for gas phase. You have PE, PP, and some fancy rubbers that you can make also depending on the topology and on the architecture of your polymer. You have slurry systems, and you have a couple of solution processes because you are able to make metallocene catalysts that tolerate very high temperatures, so above the melting of PE. So you'll have processes that run at 140. They are very rare, but they do exist. So there are solution processes. And yes, every time you develop catalysts, usually you associate an optimized process with it. So this was my introduction, very lengthy introduction. I'm sorry about that, but it's give you perspectives and the context why it's polyolefins and polyethylene in particular do matter, because they have fascinating properties just with carbon and hydrogen. Okay. What is nice is, if I talk specifically about PE, is you start with only 1 monomer. You can get it biosourced if you want. You can get green PE. Brazil does that a lot, for instance. Okay, and with 1 simple molecule, when you tune the polymerization in engineering, so the process and the catalyst chemistry, you can reach a wide range of products. Okay, so that's a big advantage. For the industry, it's ideal. Like the same raw material, and you make a lot of different products. That's very advantageous. I discussed a lot magnesium dichloride and how to make in a good way pre-catalyst. It's quite lengthy, and it's very much like a grandma recipe. Okay, you need to know a little bit, and it's basically because it's based on inorganic strategies. So you take magnesium dichloride, and you need to tune its surface. You have several strategies. One can be very physical, so you can grind it and do a lot of things like that. But because I'm a chemist, I prefer the chemistry route. So you take a Lewis base, and you will tune, okay, the number of magnesium dichloride and the way they interact with each other, depending on the choice of the Lewis base. Okay, so you will have like layers of magnesium dichloride with some Lewis base that interact with the barely Lewis acidic magnesium dichloride. And then you treat that with Tickle 4, okay? And you will get like Tickle 4 that is organized on the surface. And if you get lucky, you will have something that will turn into an active site upon alkylation and reduction. What matters is the treatment. If you want an active site, you need the treatment with aluminum alkyl and the inserting monomer. These matter, okay? And there are ways to tune the concentration of free active site, things that will turn into something useful for polymerization. And this is things that we develop in the lab, for instance. So you can add, I said that you need to tune the surface of magnesium dichloride with Lewis base. You can remove some of them with treatment with Lewis acid to increase the number of pre-active sites that we turn to useful polymerization sites. This is what we did with a variety of Lewis acid. So you can use boron-based Lewis acid, tin-based Lewis acid, silicon-based Lewis acid. You can vary the solvent, and you end up with just an increase in activity. You keep the exact same features for the polymer, okay? Exact same kinetic features, just an increase in activity, overall increase in activity, which means that you just increase the concentration in active sites. That's it. Nothing changed, okay? You can try to characterize what you did, okay? On a reference sample, you soon realize that some of these Lewis bases, once you have the pre-catalyst, okay, some of these THF, if you do a THF type strategy, they form these titanium alkoxide species. And these are very detrimental to the activation of the catalyst. if you think about a transmetallation that is possible using, for instance, boron trichloride, a Lewis acid, you will chlorinate again its bond, and this will favor the alkylation reduction process necessary for polymerization. This is what we showed those. This is a solid state NMR with a carbon, so it's a CP mass. And it shows you that you have the characteristic signals of the alkoxide, and after treatment, they are completely gone, and you form species that are apparently on the boron, but we still have to precisely assess where they are. You can also, if you follow a reduction pathway, a titanium 4 will become a titanium 3, and this you can follow by EPR, and this is what we did. So by EPR, we observed by increasing the amount of BCl3, so ranging from 0 up to 4.1, 0, 4.1, we saw the appearance of a titanium 3 species, and by doing 2D EPR, we were able to realize that this is characteristic of the titanium 3 dormant site for Ziegler-Natta. And if you do high score techniques, so these are 2D techniques where you try to see what's close to what is at the vicinity of this titanium 3, you end up with hydrogen, aluminum type of interferences. So you can determine something with the help of DFT that resembles this type of octahedral titanium 3 dormant site, because if you look closely, you realize that on this site, there is no empty coordination site. No monomer can access that. You need decoordination of one of the chlorine to turn it into something that will become a polymerization active site. And this is possible with just adding ethylene, okay? What is interesting here, a little bit of history. So this was a mechanism proposed by Rodriguez and Van Looy in 1966, so quite a long time ago. And they actually proposed something that is very similar to this active site that we hope that we showed in 2021. Nowadays, we are interested in, I like spectroscopy a lot, and we are interested not only in EPR, but also in NMR. So because you're doing a lot of reduction, it's complicated because you end up with something that tends to be paramagnetic. So NMR techniques are more difficult to apply. It's possible, but it's more complicated to analyze. And also you can look at different nuclei, and we like to do that. And these are titanium NMRs, and they show you that when you start treating the precatalyst with BCl3, you homogenize the sites, okay? And they kind of resemble something that is fully chlorinated. And that's the goal of this chlorination agent, okay, the BCl3, to increase the amount of that. If you were to do this titanium NMR without doing the Lewis acid treatment, you would not be able to observe anything because it's too heterogeneous, too many different titanium environments. Okay, so we like titanium a lot because historically it's very useful, and we try to also understand what you have to change the process to make the catalyst more efficient, the process more efficient, how you can tune all the features of your polymer. Okay, but we decided, okay, I like iron a lot. Iron is cheap, and I wanted to see if I could tune the metal in order to get an active catalyst, and this can be done. You really need the Lewis acid treatment. Without it, you have no pre-catalyst activity. It will not turn into an active catalyst. And the alkylating agent can be like conventional, or they're even better if they are aluminum hydrides. Okay, so diisobutyl aluminum hydride works really well. The activities are quite similar to what you can achieve with titanium. Okay, you're gonna, instead of treating a magnesium dichloride support with Tcl4, you will treat it with iron chlorides. Okay, and you end up with a catalyst that can be very active and almost as active as some very good titanium catalyst. So this is a reference catalyst we have in our lab, and you can reach values that are comparable and and better than chromium or Phillips catalyst, for instance. A little bit of spectroscopy, as I said, the role of the Lewis acid treatment is once again to remove the alkoxides. So these are these bands. They correspond to the rates that you would form upon removing all the iron oxygen bonds that you would have formed on precatalyst synthesis. This is to give you a rough picture. We do believe that we start with an iron 2 chloride center, and something happens to this iron 2 chloride center when we the alkylation reduction. Okay. Just a comment about the mass Bauer. So we suspect that we are generating iron hydride species that are key for the polymerization. That explains why aluminum hydrides are a little bit better as activators compared to TA. You can reach very high molar masses polymers with these. So these are like more than 1 million grams per mole PEs. And you can even produce isotactic PP using this type of catalysis. Okay, I'm going to skip that. Not that important. Okay, I just want to mention a quick, if I can get 5 minutes. Sylvain, you allow me 5 minutes? Okay, perfect. I was a little bit long at my introduction. Sorry about that. So you know that because we are making so many of these polyolefins, they do accumulate. They have fantastic properties, but we need to deal with their end of life. And I just want to give you a short insight of what we can do about it. Okay. So I'm not going to discuss all the recycling strategies. I hope some of my colleagues will present that, but we have too many of them that are landfilled at the moment. Some of them are incinerated, but you get only energy from that. And only 9% are recycled. I already mentioned that. Many strategies to do a chemical recycling. I'm not going to discuss mechanical recycling. It's very useful. The problem is it's usually a downcycling strategy. So you start losing properties. With chemical recycling, you can think of it as, okay, I have polymer waste. And instead of doing conventional refinery, maybe I can turn these into raw materials and making new matter with it. And there are many things that you can do with polyolefin waste because they look like, I would say, fancy crude oil, basically. And there are many processes that can turn these very long crude oils, okay, into something useful. Okay, of course, pyrolysis, but then you can do very selective oxidations to turn them into like a specific length or to oxidize them, to introduce like polarity on the chain. And all of these are very useful. Our strategy is a little bit different. We want to precisely introduce things that can be used into compounding, for instance. So just in saturation. And I'm going to only mention introduction of unsaturation today. We do a little bit of oxidation. I'm going to mention only unsaturation today. If you introduce unsaturation on a polyethylene backbone, after that, you should be able to do metathesis and to chop them down to something smaller. And this is what we do, and we do that with several catalysts. We do that with iridium. So iridium is costly, but you can lower the amount that you use because these are very robust catalysts. You just need to be able to heat the system to 150, 200 degrees, and you are able to introduce double bonds. And after that, by metathesis, you can cut precisely the polymer. So in the lab, we do that. Sorry. We do that very efficiently with, okay, do that very efficiently with iridium, and we introduce trans double bonds and some cis double bond, and this is characteristic of what iridium can do. It will usually give you a little bit more trans, especially at 200 degrees, and you have several strategies to make the catalyst very robust, and one of it is to introduce a little bit of base to prevent catalyst decomposition. Something that we do also is to follow where we locate these double bonds, and they are statistically distributed. So there is a continuous decrease in crystallization temperature when you increase the amount of double bond, okay? And when you chop them also, you will see that you can confirm that that there is a statistical distribution of these double bonds. You can do this process in a ball miller. You need a hydrogen acceptor. It makes it more efficient. And you can introduce a lot of double bonds, a lot of trans double bonds. You can change the metal. You can turn to ruthenium rather than iridium. And this has a lot of advantages because it gives you a little bit more cis product when you turn to ruthenium. This is also characteristic of what ruthenium can do if you want to go cheaper than iridium. And we are trying right now to go even cheaper than ruthenium. Okay. When you chop them, you just use ethanolysis, a metathesis catalyst that will cut all the chains and give you alpha olefin chains. Okay, so you remove almost all of the trans double bonds, and you end up with something that is only an alpha olefin. And by looking at the way the distribution moves to lower molar masses and unimodal strategies, you know that it's statistically distributed along the chain. You can do cross-metathesis to introduce functions. I'm not going to describe that too much, but because I don't have time. And this brings me to my final slide. I rushed a little bit, sorry. And I just wanted to give you the strategies that we are using at the CP2M lab. So you need catalysis, okay, to make polyolefins. You need to understand how you make the catalyst and how the active center works if you want to tune the polymer that you make in the end. Okay, so if you want to make chain longer, you can go to iron, for instance. You can mix the metals if you want to tune the properties. And then if you understand that really well, there is also a way to harness catalysis to deconstruct the polymer. But it would be foolish to think that deconstructed a lot is worth it, especially if you compare it to crude oil. So it's probably better to keep the overall backbone and to be very selective in where you introduce functions and not overdo it, because otherwise you need too much energy if you want to deconstruct fully. This is a strategy that we use also for silicones, and in that case it's very different. First of all, because the product is more expensive, okay, and because in that particular case, you don't need to go back to metallurgy steps. So recycling is very efficient, and going back to monomers for silicones is more interesting. And with that, I just want to thank again the students who did the job. So Adamou, Felipe, and Mathieu, Sébastien and Vincent, who are long-term partners, and Vincent in particular, and collaborators and funding agencies, and you for your attention. And sorry.
Thank you, Jean, for this very interesting introduction and very insightful talk. So we're running a bit late, but we could have some questions in the audience if you want, or remote question as well. So if you have some questions. I have one. When you insert a double bond in this polyethylene, I mean, I'm sure there's a compromise
yes.
of, having too many double bonds regarding the properties, or
yes.
not enough to do the recycling. So could you give us some information regarding the compromise of properties and?
So we try to overdo it. So we try to push the system to get many double bonds, but then the product, they get difficult to isolate because it's so easy for cross-linking to take place. Okay, so we are running the dehydrogenation between 150 and 200 degrees. If you put more than 50 double bonds per 1,000 carbon, then you run into cross-linking issues. Less than 50, okay. 40, 30, this is no problem. It's more when you want to push it, then it's very hard to control cross-linking. Okay, so you do get cross-linking very easily. It's not going to be reversible, but you do get cross-linking very easy.
Okay, well, thank you very much. Are there any other questions in the audience? If not, yes, Camille, yes.
Thanks for your presentation. So you mentioned that if you add Lewis space,
yes,
you accelerate and you increase the productivity. Can you imagine a functional Lewis space with a double bonds, which can be integrated into the backbone? Because it's pretty hard to have functional polyethylene.
So the question for remote guys was: is it possible to add the Lewis catalyst in the polymer?
Yes, basically. So all the ligands that I mentioned. So basically, when I say they are mostly inorganic ligands for supported magnesium dichloride based catalyst system. Okay, you do have some Lewis base, and we tune by adding some Lewis acid to remove some of these Lewis base. The problem is this does not end up at the end of the polyethylene chain. The only thing that ends up is the first alkyl that comes from the aluminum alkyls. Technically, if you were to prepare an aluminum alkyls that is functional, okay, you're very good at it, and you know that the three alkyls behave the same, and they all bear the same function. It's not easy, but people have tried. You should be able to have kind of a functionalized PE. But remember, that works for only one chain, and you have a lot of transfer to hydrogen. So a lot of the chains will not be functional. That's the problem with these type of strategies, okay? If you were to do that, it's better to do CCTP, so control chain transfer polymerization, where you have an alkylating agent, where you do reversible transfer back and forth between the alkylating agent, but this is a process control. And in that particular case, yes, if you have a functionalizing transmetalliting agent, you can have functional polyethylene in particular. Christophe Boisson, Franck D'Agosto, they do that very, very nicely. Thank you.
So thank you very much once again. Let me join and thank again our first speaker.